When we speak about exocytosis and endocytosis, we're speaking of very generalized processes. But as I said earlier, there are specialized forms of endocytosis as well. Phagocytosis is one of the specialized forms, and that's because we reserve the term phagocytosis to describe any kind of endocytosis of large molecules, large materials. Remember, we said lower eukaryotic organisms, more primitive eukaryotic cells, are going to use endocytosis to bring nutrients or food into the cell. Now, depending upon whether they're bringing in small molecules or large materials, again, greater than about 1/2 of a micrometer, that's the size limitation there. If they're bringing in small materials, we would call it endocytosis. If they're bringing in large molecules, we would call it phagocytosis. The same vocabulary applies to higher eukaryotic organisms. Remember, we said immune cells sometimes perform a very generalized type of endocytosis because they surround and consume and destroy pieces of material that are in the body that don't belong there. They're foreign to the body. But sometimes those cells actually surround and bring in living organisms. I mean, think about, for example, immune cells encountering bacteria. Bacteria are generally greater than 0.5 micrometers. Many bacteria are 1 or even 2 micrometers in size. So we would describe that as phagocytosis, bringing in large materials from the outside. There are even cells in higher eukaryotes called fibroblasts that perform phagocytosis. Fibroblasts are sometimes tasked in a cell with remodeling tissue. In other words, after tissues are injured, and after the healing process has occurred, sometimes the tissue needs to be remodeled. Think about, for example, the last time you had a big scab somewhere on your skin, and that scab slowly retracted and eventually disappeared, and then over time, even the small scar that was remaining disappeared. The same thing happens in internal tissues when they're injured, including your bone, for example. After a fracture heals, there's what we call a callus at the fracture site, a bulging of tissue that doesn't belong there, and the fibroblasts will be tasked with cleaning that up and returning the tissue to its normal anatomy. Well, that process of remodeling tissue involves fibroblasts performing phagocytosis. They are bringing in large pieces of that tissue in order to remodel it. So the difference between generalized endocytosis and this specialized phagocytosis is simply the size of the material that's coming into the cell. If it's smaller than 0.5 micrometers, we call it endocytosis. If it's larger than 0.5 micrometers, we call it phagocytosis. Now, another specialized form of endocytosis is called pinocytosis or pinocytosis, as it's sometimes pronounced. Pinocytosis translates as the drinking cell. So pinocytosis is the bringing in of only liquid material into the cell. Now, of course, there may be some things, some small molecules, some ions dissolved in that liquid. We would still call it pinocytosis, but pinocytosis refers to endocytosis of liquid only. The last form of specialized endocytosis that we need to be familiar with is called receptor-mediated endocytosis, or RME. And we're going to take a few minutes to talk about RME. This is a form of endocytosis that is not general. In other words, this is going to be a process where specific chemicals, specific molecules, what we sometimes call ligands or ligands, are going to come into the cell by binding first to a receptor. And that is going to initiate this special type of endocytosis. Let's take a look at the drawing on this slide. This drawing shows the difference between phagocytosis, pinocytosis, and receptor-mediated endocytosis. If you start over on the left, the artist has drawn this area as the inside of the cell. They've drawn a gold line to represent the plasma membrane, and then this area represents the outside of the cell. So there's fluid in this external environment, and in that fluid there are some small dissolved molecules, and there's also this great big red particle. When this particle is taken into the cell through endocytosis, because it's so big, we're going to call this phagocytosis. It's still a generalized process. In other words, there's nothing in particular about this particle that is causing this process to happen. It's a generalized consumption of this particle. But because the particle is large, we're going to call it phagocytosis. Now, pinocytosis is different because in pinocytosis, there is no particle coming in, small or large. This little blue thing right here represents some very small molecule or maybe some ions that are in the fluid. But what's coming into the cell through pinocytosis is the liquid that's outside of the cell, not some particle itself that's being captured. Finally, let's look at receptor-mediated endocytosis. What you're seeing here is these little sort of Y-shaped blue structures jutting off the surface of this membrane. And you're also seeing some representations of proteins on the inner side of the plasma membrane. You can see some of these smaller molecules, the stars and the blue dots. The stars are actually able to bind to those blue Y-shaped receptors. And it's the binding of the star, or what we can very generally call a ligand or a ligand. It's the binding of the star to its receptor that's going to cause the infolding to start, and eventually those stars to get captured into a transport vesicle. So phagocytosis is this process that brings a large particle or particles into the cell. Now, phagocytosis is non-specific in the sense that there is no particular receptor, no specific receptor that this large particle is binding to. Instead, it's binding to the membrane very generally. It's going to come and interact with protein in the membrane just very generally. And when that large piece of material binds to the outside of the plasma membrane, its size is going to trigger something really interesting to happen. What we refer to as pseudopods, or sections of the membrane, are going to start to fold outward and reach up and around this big particle. I'll show you a picture of this in just a minute. In other words, rather than having the plasma membrane invaginate, this time the plasma membrane is going to reach outward into the extracellular area, up and around this big particle, using what are called pseudopods. The material will then be pulled into the cell, creating what we often refer to as a phagocytic vacuole, or what's also called a phagosome. Once the phagosome gets into the cell, in other words, this unique transport vesicle gets into the cell, it's going to have the same thing happen to it that all newly formed transport vesicles encounter. It's going to bind with an early endosome. They're going to merge and become a late endosome. And then that's going to mature into a lysosome. And whatever material is in there is going to get degraded. Let's take a look at this picture that represents the process of phagocytosis. Again, the orangey, sort of peach-colored area represents the inside of the cell. This represents the plasma membrane. The blue area represents the outside of the cell. And this diagram is meant to be read from the left to the right. So if you start on the left, you can see this big object outside the cell. It happens to be a bacterial cell. And this bacterial cell, which has proteins on its membrane, is going to come and interact with proteins on the plasma membrane. This is a very sort of non-specific interaction. In other words, the proteins on the plasma membrane are not receptors for this particular bacterial cell. This is just a non-specific type of interaction between proteins, but that binding interaction is going to cause this to happen. Regions of the plasma membrane are going to extend upward and outward into the extracellular environment. These are called pseudopods. Pseudopods translates as false feet. Notice that as the membrane extends upward and starts to surround that bacterial cell, more and more interactions are happening between protein on the outside of the bacteria and protein on the surface of the plasma membrane. Eventually, those pseudopods are going to meet each other and they're going to fuse. So what's created at that point is a new transport vesicle. That transport vesicle, or what we more specifically call a phagosome, or a phagocytic vacuole, that's going to come into the cell. That's going to bind with an early endosome and become this newly formed thing that we're going to call a late endosome. And then that late endosome is going to mature into a lysosome, and the enzymes inside are going to digest that bacterium. Now, don't worry too much about this back and forth arrow designation. The idea the artist is trying to convey is that sometimes multiple early endosomes will come in contact with the phagosome. The key thing to remember is that early endosome or endosomes are going to fuse with that phagosome, creating a late endosome and then a lysosome. And the lysosome is what's going to eventually digest that material, that large material. Now let's turn our attention to receptor-mediated endocytosis, or RME. And again, this is a form of endocytosis where a specific molecule outside the cell is going to bind to a specific receptor on the surface of the cell. Now, in order for a molecule to interact very specifically with a receptor, it has to be relatively large. In other words, something very small, something the size of, say, an ion, is not going to bind to a receptor and come in through receptor-mediated endocytosis. That just doesn't happen. These are relatively large molecules. Now you might say, well, if they're large, why don't we call this phagocytosis? And the answer is because of the specific nature of the interaction between the molecule and a receptor for the molecule. There is a very particular receptor for these molecules. Now let's look at some examples of the ligands that tend to come into cells through RME. One good example is cholesterol. Cells can take cholesterol in using RME. Various hormones can come into a cell through RME. Growth factors. Things like enzymes can be imported into a cell. Even bad things like toxic materials can come into a cell through RME. So, each one of these molecules, each of these molecules that comes into a cell through RME has its own receptor on the surface of the membrane. And it's the binding of the ligand to its receptor that's going to trigger RME to occur. So, of course, these receptors that are involved in RME are going to be exposed to the outside environment. In other words, they're going to be in the outer monolayer of the plasma membrane so that the molecule or the ligand can come and bind to them. These are generally relatively large materials, so upwards of maybe 100 nanometers in diameter. So this would be 0.1 micrometer. Technically not even large enough to be called phagocytosis, and certainly we wouldn't call it phagocytosis because of the specific binding that's going on. Now here's where receptor-mediated endocytosis gets very complex. When the ligand binds to its specific receptor on the plasma membrane, that binding causes a shape change, as we've talked about. We refer to this new thing as a ligand receptor complex. It's the ligand plus the protein receptor that are now stuck to each other and have changed shape. What's going to happen next is very strange. Remember from our earlier discussions of how proteins sit inside plasma membranes. Remember that we said that proteins are freely movable for the most part inside the membrane. They can float around through the phospholipids, just like a beach ball would float on the surface of a pool. So the ligand receptor complexes are going to start doing just that. They're going to move laterally in the membrane. Remember, lateral diffusion is quite common in membranes. We see things move within a monolayer quite commonly. We don't tend to see them flip from monolayer to monolayer, but we do see them move side to side or laterally within a monolayer. And that's what the ligand receptor complex is going to do. It's just going to move side to side until it encounters a very specific structure called a coated pit. Now, we haven't talked about these yet, but these are areas of membrane that are full of a particular kind of protein. About 20% of a membrane's surface is full of these coated pits. Now, the reason we call them coated is because they are full of what are called coat protein. the ligand receptor complex is going to just laterally slide around through the membrane until it hits one of these pits, and then it's going to stop. And as more and more and more ligand receptor complex arrives at the pit, that's going to trigger something to happen. And that something is on the inside of the membrane. More and more coat proteins are going to arrive. So this is one of those cases where it's about the accumulation of material. As more and more ligand receptor complex arrives at these coated pits on the membrane, as more and more of it arrives and accumulates in the pit, that's going to trigger more and more coat protein to come to the pit. And it's the arrival of the coat protein and the buildup of the coat protein that is going to trigger the invagination to occur. The membrane will slowly, progressively fold inward. A vesicle will pinch off, and now you've got a new transport vesicle. But this is a special kind of transport vesicle because it's covered in these coat proteins. So we refer to this kind of transport vesicle as a coated vesicle. Now, while that vesicle has these coat proteins on top of it, not much happens. But eventually the coat will be released. And at that point, it's just any other new transport vesicle. It's going to bind to an early endosome. It's going to mature into a late endosome. The pH is going to drop and drop and drop. Now, inside this new vesicle, remember, and I'll show you a picture of this in a minute, inside this new transport vesicle is that ligand. But remember, it was stuck to its receptor. We called it a ligand receptor complex, in fact. So as the pH drops down and drops down, it'll hit a level that will trigger the ligand to release from its receptor. The receptor is going to get recycled. The receptor is going to get recycled back to the membrane, in fact. The ligand is going to get trafficked somewhere in the cell. Let's take a look at this complex process. Now, this is a very busy diagram. We'll walk through it together, though. You're looking at a cell surrounded by this gold line that represents the plasma membrane. The interior of the cell is that peachy color. The exterior of the cell is in blue. Now this diagram is read by following the numbers and following the thick blue arrows. So we're going to start right at number 1, where a ligand, maybe it's a hormone, maybe it's cholesterol, it's going to come in and it's going to bind to its own very specific receptor on the surface of the cell. That's what they're showing us right here. The purple represents the receptor. The ligand is shown as a little sort of yellow gold hexagon. Now remember, when this binding occurs, the protein receptor is going to change shape. So now we have a newly formed structure in the membrane. It's called a ligand receptor complex. That complex is not going to sit still. Like all proteins, it's going to travel laterally through the outer monolayer until it hits a region called a coated pit. Now these pits get their name because on the inside of the cell, the pit is lined with protein called coat protein. Now there are many different kinds of coat proteins. We're not going to talk about specific coat proteins in this course. As the ligand receptor complexes arrive in the pit, they stop their lateral diffusion. More and more and more of them will arrive and fill up that pit area. As more and more ligand receptor complex accumulates in the pit, it will attract more and more coat protein to the inside of the membrane. Now, the artist has drawn in a few different types of coat protein here. You'll notice one is called adapter protein, one is called clathrin, one is called dynamin. Don't worry about those names. Just know that more and more coat proteins are going to arrive and are going to bind on the inside of the membrane, the inner monolayer. Eventually, there'll be enough coat protein to trigger this, to trigger the invagination of that area of the membrane. That will pinch off and create this, what we might ordinarily call a transport vesicle, but in this case is referred to as a coated vesicle because it is covered in coat protein. Eventually, this vesicle is going to get uncoated, and the only thing that is left now are these ligand receptor complexes in the membrane. The uncoated vesicle is going to merge with early endosomes, and it's that merging that will trigger proton pumps to bring hydrogen ion inside. That hydrogen ion is going to lower the pH, and eventually it will hit an acidic enough level so that the ligand will be released from the purple receptor that is still sitting in the membrane. Now we have free ligand in here, and it can be trafficked off to whatever destination in the cell it needs to go to. Meanwhile, the receptors for that ligand, what's shown in purple, can be sent right back to the plasma membrane to be used again as a coated pit. So this is a situation where the merging of the coated vesicle with an endosome didn't go to fruition, did it? It didn't go all the way to a late endosome and to a lysosome. You see, this ligand is not intended to be broken down and recycled. Now, there might be other ligands that come into a cell that are destined to be broken apart some way. So there are some ligands that come into a cell through RME that will eventually get degraded. But other ligands come into a cell through RME and remain intact. In other words, there are different fates for different molecules that come into a cell through RME. Some of these molecules even end up being released on the other side of the cell. Remember, some cells are polarized. Some cells have an apical surface and a basal surface. So it's possible for certain ligands to come in through RME on the apical side of the cell, only to then be released intact on the basal side of the cell, so that the ligand can function somehow inside the deeper tissue. Different molecules that come into cells through RME can have different fates within the cell. Some of them are going to experience the process where the early endosome matures into a lysosome, the acid hydrolase enzymes are activated, and the ligand is digested or degraded. Other times, the ligand will be taken to some specific destination in the cell, intact. And still other times, the endosome will travel to another region of the membrane, and the ligand will be released through exocytosis, a special form of exocytosis that we can call transcytosis, with the trans term meaning other or opposite. The ligand came in through the apical side, through RME, and was released on the basal side through transcytosis. I want to say just a couple other things about RME before we finish today. There are some regulatory variations in this specialized form of endocytosis. There are some coated pits on cells that contain receptors for ligands where the receptors are already concentrated in the coated pit. Remember, we said the ligand binds to the receptor and creates a ligand-receptor complex, and the ligand-receptor complex then goes through lateral diffusion until it encounters a coated pit. Well, sometimes the receptor is just located in the coated pit already. So when the ligand binds and the ligand receptor complex is created, there's no need for lateral diffusion because it's already inside the coated pit. There are other instances of RME in cells where receptors are concentrated in the coated pit areas and they undergo what's called constitutive internalization. Remember, we said normally more and more and more ligand receptor complex needs to arrive at the coated pit so that more and more and more coat protein can be attracted to the pit, and that is what triggers invagination. There are some coated pits in cells that don't wait for more and more coat protein in order for invagination to occur. Instead, the invagination just occurs on a regular basis. The invagination occurs on a constitutive basis. It just happens. So it brings in some amount of ligand receptor complex into the cell, but it doesn't wait until there's lots and lots of ligand receptor complex. That's what we call constitutive internalization in RME. I said earlier that you don't need to worry about the different roles of different coat proteins in this course. I just want to expose you to some of the names. There's one called clathrin, there's one called adapter protein, there's one called dynamin that we saw in the earlier diagram. There's one called ADP ribosylation factor, or ARF. There are coat proteins called COPI and COPI2. There are some called caveolin. That is the coat protein that happens to be involved in the RME process for cholesterol. There are lots of coat proteins, and more of them are being discovered all the time. The important thing to remember is just their general role in the process of RME. We'll finish up today with this slide and this set of images. This is a time lapse of RME occurring in a cell where the material that is serving as the ligand is actually a type of protein found in the yolk of eggs. So what you're looking at in these images is membrane and coated pit. You can see in the first image on the left-hand side that The yolk particles are all sitting inside this region of the membrane shown here. They've all gathered, all of this dark material right here has gathered in this little region of the membrane that is a coated pit. You'll notice that while this is the membrane, on the inside of the cell, which is on the right-hand side, there are fuzzy, dark-colored structures binding to the membrane. These are coat proteins. More and more yolk particles arrive as ligand receptor complexes, and that attracts more and more coat protein. And that arrival of coat protein causes this to happen, invagination. Eventually, the invaginated membrane is going to pinch off, creating this coated vesicle. Once it's pinched off, all of the ligand receptor complex, all of that yolk protein, is on the inside of the vesicle, and the coat is on the outside. This is what we call a coated vesicle.